So far in class, we have focused, at least in the discussion of formalism, on operators with discrete eigenvalues. So what I wanted to do here is taking a look at operators that have continuous eigenvalues. And the examples that come to mind are actually the position and momentum operators. And it's rather straightforward to extend our discussion of the postulates of quantum mechanics to continuous eigenvalues for Hermitian operators. So let's do that. So in the discrete case, we discussed that we have an eigenvalue equation for any operator. So Qn is equal to eigenvalue times Qn, and here, n was labeling the different eigen states and eigenvalues and was running, for instance, over the integer numbers. And in the continuous case, this looks just the same. Here the eigenvalue equation will be Q lambda equals lambda times Q lambda. And maybe the only difference is here that, lambda is maybe a convenient labeling the eigenstates with the eigenvalue itself is a convenient way to do that, and lambda will be a continuous label. We've learned that we can choose our eigenvectors to always be orthonormal to each other. So that means if I have my eigenstates Qn and Qm, and now I'm also assuming that we have normalized all of these, we can choose these eigenvectors always such that they are mutually orthogonal, and then if we normalize them, they are orthonormal. So this equation is true. If the eigen states are continuous, then we'll have that, or this relationship will take this form here, where instead of the Kronecker delta, we actually have a delta function. So we transition from having the Kronecker delta to the delta, to the Dirac delta function to describe that the eigenstates are orthonormal. Another property is that we learned that the eigenstates to an observable form a complete basis of the Hilbert space the observable is operating on. And so that means that any quantum state in my Hilbert space I can actually decompose or represent in terms of a linear superposition of the eigenstates to the observable Q. And if we, however, have a continuous set of eigenstates and eigenvalues, this will take the form, the sum will take the form of an integral. Like this. And then the components in this decomposition I can write in the following way. Okay, so here for the discrete case, we know that what we got to do is to obtain coefficient Cn, I need to calculate the inner product of the corresponding eigenvector with psi. And so in the continuous case, this is actually just going to be the same. Only what I'm obtaining, since my label lambda is continuous, I'm actually obtaining a function of lambda. So just like this. And then we have learned that the meaning of these coefficients Cn here is if I take their absolute value squared, they give me the probability of measuring a particular eigenvalue. So we had learned that the probability of measuring eigenvalue lambda n is equal to absolute value squared of the corresponding coefficient Cn squared. And so this, in the continuous case, then becomes the probability to measure lambda times d lambda is going to be equal to the coefficient c of lambda absolute value squared d lambda. The reason I'm including the intervals d lambda here is that since now lambda, or since the eigenvalues now are continuous, p of lambda is actually not a probability, but is a probability density. Okay, and how can I see this? Also, if now I sum all these coefficients, I get 1. When my quantum, assuming a normalized quantum state, and likewise here though, instead of a sum, I have an integral over c lambda absolute value squared, and that should give me 1. And the fact that I have an integral here, so I'm integrating over absolute value of c of lambda squared, also tells us that really c of lambda absolute value squared has to be a probability density.